Now, as Mr. Downey was kind enough to remind us that the relationship between the power and how it's represented on the screen is a product of the resolution bandwidth. But once you have established with your tool sets what that relationship is, then you can start to look at devices inside of homes and determine what their received power is. Now, these are examples of just flat loss. Now, this isn't cable loss due to attenuation, because normally you'd see that attenuation being frequency dependent as a lot of slope at the receiving device. But in this instance, the responses are relatively flat. They're just at low power. So in these scenarios, with 0 being represented here by this green line at approximately -17 with 117 resolution bandwidth, we're looking at, -20 signal powers at these devices. So these devices have very low power, typically due to a couple of things. Excessive flat loss. They put a splitter in the house to hook up another outlet, excuse me, and decrease the power to a particular device, or they could have had an active device like a house amp that failed or came unplugged and is now providing excessive flat loss. So when you see something like this is not tilt or cable loss. This is excessive flat loss caused by something in the downstream path that is adding additional attenuation to the downstream. Okay, so this one's the opposite, right? So this is tilt. It could be a couple of different things. This could be good old-fashioned cable attenuation, right? You've got a really long drop. Let's say you're at a terminating tap before a 2-tap that has some reverse tilt just because of the long feeder from the amplifier. So the natural attenuation of the feeder cable, you may have reverse tilt coming out of the tap, and then you throw that RG11 drop to get 1,000 feet back to this customer at the end of the line because they want service, and at the end of it you've got a pile of tilt, right? So we can determine that somewhere along the way it's also possible that we have an amplifier misaligned, right? You, instead of having 10 dB of forward tilt on your amplifier, you only have 2 or whatever. But there's an easy way to identify whether it's excessive flat loss or if it's just natural cable attenuation loss, either through the distribution plant or the drop system as a result of a lot of cable. Okay, so that's just tilt. Okay, we already referred to compound impairments, right? It's important to understand each of them individually so that when you see them combined, you can start to pull out, multiple impairments. Like this first one's a great example. It has a big suck out here right around 350 megahertz or so, and you also have high-end roll-off. So poll the audience. What do you think that is? One cause, two causes? What are the causes? There might be a prize here, by the way. This first one. So we've got a big suck out right here. And you think it's 2 causes? What do you think they are? I'll agree with the water part. The loose seizure screws typically tend to show up with that low end roll off, right? The high end roll off typically tends to be water. And the suck outs typically tend to be corrosion in a passive device. So imagine that we have like a tap and a coupler, together out in the plant. We get some water in them. The water pools, causes that high end roll off. We get some corrosion that causes the suck out. It's likely, 2 different impairments. They may or may not be associated with the same place, but it's possible, right? When you think about what causes each one of those in turn, or you can see water in the cable, right? Say it's an underground cable that's got a nick in it, got some water intrusion, and maybe that water migrated into a tap or a connector or, a splitter, and maybe that corrosion then caused the suck out. So that's why we spent so much time on the individual impairments and connecting them to causes, because now when you look at them in compound, you can start to say, well, hey, maybe now I know I have 2 different things. Again, we have something that looks like a periodic wave here, right? And then we have this big, huge suck out right here. So that's 2 different potential impairments. Here we have a lot of ingress, right? We see this huge amount of FM ingress right here, some VHF ingress, and we've got a standing wave that looks like it may be non-periodic, could be some water. So as you start to kind of pile these impairments together, you get some really unique responses because there are multiple impairments. And again, all the device is telling us is it's representing how the downstream energy is being received at the front end of that device. So this is any combination of all the stuff that we've just talked about. Everything in the kitchen sink. Now, I keep talking about all of these responses and how they're defined and what they look like and what they point back to. But the reality is all of the images that were in this presentation were symptoms that are displayed in intelligence tools. Now, all of them were caused by something. So when we go out and we fix No, we go out and we fix an impede standing wave. Do we actually fix a standing wave? It's mismatch because that's a crack or a loose connection. But there's a distinct relationship between causes and symptoms. Now we can talk about the alphabet soup of symptoms because there's a million of them. You know, FEC, SNR, MER, BER, CNR. There's a bunch of different symptoms that our tools measure. The real trick is to look at the causes or the symptoms and say this is typically caused by, I will say, one of two things. All the impairments that we looked at and talked about today, in my experience of almost 30 years, come down to one of two things or a combination of the two. And one is impedance and two is shielding integrity. Especially think about ingress. In the coaxial system, the shielding integrity is measured in how much energy the coax itself can withstand, and that is its shielding integrity value. Now, when the shielding is impaired or degraded, its value goes down and it can no longer withstand the pressures from all of that energy. So what happens? The energy overcomes the shielding integrity and it gets into the system. Now, in a lot of cases, the signal inside the system gets out, and that can be measured as leakage or egress. But the important thing to know is that the cause is actually a shielding integrity breach. So why is that important? Well, if I look at all of my full band capture traces and I recognize that all of the customers in this neighborhood have this same downstream ingress energy showing on their devices, right? And I look at my system design prints and I say, okay, well, they're all fed off of this span of cable or this amplifier or this whatever, figure out what they have in common. Well, now when I get out of my truck, I know what I'm looking for. I'm looking for a shielding integrity problem. That could be a squirrel tube. That could be a radial crack. You guys ever look at the power lines above the cable and overhead? You old cable dog, you know what I'm talking about, right? If you see that pickle that indicates a splice in the power, because that means at some point the power broke and it came down. Now, if it's in mid-span, you'll typically see broken lashing wire there too, right? Or a couple of bug nuts up there where somebody went out and put the lashing wire back up. Well, there's probably also some burn holes in the top of the cable. That's just a shielding integrity problem that can lead to these symptoms, right? But the physical cause is the holes in the jacket that were caused by the power line that came out or whatever. You look at the squirrel, you look at a drip loop that was poorly formed over years, right? And sometimes you can tell even underneath the strap, you can see the cable is a little sharper than it maybe ought to be, right? There's likely a crack underneath of that strap. Now that's a shielding integrity breach. It's also an impedance mismatch. So now we're into that compound impairment category, right? We've got that radial crack that's allowing ingress in, but now it's also creating these reflective cavities of different sizes depending on where the crack is. So as we go all through this, I want you to recognize what the symptoms are and start to connect what the shape of the response is to what the symptom is. Is it water? Is it a periodic standing wave? Is it a compound impairment? Is it ingress? And then draw the next conclusion to the cause. Now, the easiest ones for me are always the resonant peaks, because I know I'm looking for an amplifier, right? And different amplifiers tend to have different shapes of resonant peaks. So, you know, I've seen C-Core, I love C-Core, but the C-Core FlexMax stuff has a very distinctive resonant peak. And did anybody ever do like layup stick repairs back in the old days? You just, yeah, you get your layup stick out of the track and you whack the housing and the problem goes away. Well, at least for a while until your buddy's on call, then he'll get it. But yeah, things like resonant peaks, you can do the layup stick fix, or you can just boom up there and tighten everything up and it probably goes away. Now, if there's corrosion in the housing or on the seizure assemblies inside the housing, you probably want to wreck that out in the overnight and replace it. But, you know, you start to get a sense where when you look at an impairment and how it's localized and how many customers it's affecting as to what the causes are. Because ultimately the causes are the important part. And I would argue that most of the things that we looked at today is either a shielding integrity problem, turn your leakage detector on, you'll probably find it, or an impedance mismatch. Okay, so again, talking about the alphabet soup of symptoms. Now, this is my personal evaluation of like how to break certain symptoms into buckets. We talked about SNR, MER, CNR. There's another one here that we haven't talked about, but it's this carrier to interference noise ratio. Remember when we were talking about the ingress and looking at our downstream, and you may not see the carrier sticking out, right? You may not see the ingress exceeding the level of your carrier, but it's hiding underneath of it. And that'll show up as a degraded MER on that carrier. Now that's actually the carrier to interference noise ratio. If the carriers on either side of it are the same amplitude, so you don't see a frequency response problem, but these ones have 40 MER and this one has 23, well, there's probably some ingress underneath that carrier you just can't see, right? So you need to kind of think under the carrier and say, as I'm scanning across my MERs, I've got some that stick out that look kind of bad, right? Likely there's a shielding integrity problem in the coax somewhere that's allowing ingress under that carrier that's not visually represented as a peak, but it's a carrier to interference noise ratio issue. So I kind of break these into three different buckets. The signal integrity modulation error ratio and carrier to noise, those impairments of signal noise ratio, those indicate that the quality of the medium or the cable itself. I think about the carrier interference noise ratio, that peak to valley or frequency response of specific devices. When we think about them in the hard line, they show up as suckouts, ACPs, waves. But the leakage is also a great indicator that's not necessarily associated with full band capture or PNM tools, but it's another indicator that you have a shielding integrity problem that will also manifest itself as something else in our PNM tools. And then lastly, there's the data integrity impairments. Our networks anymore are data transport networks, right? We're carrying bits, ones and zeros, electrical signals upstream and downstream. That's what our networks do, right? So we can measure the data integrity and it'll show up as FEC, you know, pre or post bit error correction. Those are data packets that are either impaired or lost. So when you start to think about the types of impairments, you have your signal quality impairments or your signal integrity impairments. You have the impairments that are affected directly by the medium or the cable itself, and then the data integrity impairments that are the result of one of these other impairments showing up as lost packets or corrected packets. So that's just the way I visualize the different types of impairments.